We get a few minutes to make a little commercial break from everything, so we give just a little sense of what Eric does and what our capabilities are. Do we have yet?
You should be. There you go. I think you should be up.
So we've been around for 60 years. We had our 60th anniversary birthday party a couple weeks ago. We're pretty proud that we're still, in business doing what we do. We don't like to do the way I want, but we do engineering, architecture, interiors design. We're kind of an all service engineering firm. But the thing that's different about us is we do some things that are quite unique in terms of what our markets are. We are in the national security market, the energy market, sustainable infrastructure, and my favorite, life sciences. I'm the leader of the life sciences business unit for America, so that's where my expertise and passion is. We're kind of spread around the country and in some international locations as well. I won't go through the list. I think you can see that we're pretty well spread out. And we work all over the world as well. We have, especially the life sciences team, we have work going on in Australia. We actually have a project in Antarctica right now for the National Science Foundation. We're working in New Zealand, in the UK, and in the former Soviet Union. So we have really been in different places taking our skill sets abroad. We are, I'm not going to go through this very detail, but we do facility design and commissioning and validation. As you know, these buildings get more and more complicated year by year, so it takes a lot to get them working just right the way they should, and commissioning and validation goes into that. We work for U.S. federal agencies, for universities, for private sector clients as well. We really think that leadership in the market is important for us, so we try to be one of the first names that comes to your mind when you think about who can design and do a great job designing a biocontainment laboratory. And the phone actually rings quite often with people saying, you know what, I've got a laboratory, I can't make it work, it can't certify, the airflows don't work, the control systems aren't working, the designers can't fix it, the constructors can't fix it. And we've been called on a couple of those occasions to help sort out the issues. And Ken and Eric are a great example of guys that are smart to figure those things out. A couple quick project examples. I mentioned the New Zealand National Biocontainment Laboratory, just going into construction right now. It's their first big biocontainment laboratory in Wellington. The Turbine Institute is a project over in the UK. We're doing validation and commissioning on that very large project. They work with foot mouth and various other dangerous pathogens. Did I spell it wrong? Yeah. Sorry, this was an internal presentation. I should have caught that. So sorry.
We like it. It's Friday afternoon.
We're working up in Canada for the Atomic Energy Canada Limited. It's a work for them, ACL, Chalk River, and USAMRIID. So you know about the projects and the facility at USAMRIID. We're working there to commission their brand new sample replacement facility. Notably, and on projects which both Ken and Eric have worked on, the NBAP project in Kansas, which is just now in construction. We were the designers of the BSL-3 ag component of that, along with other teams that designed other pieces of it as well. So with that, commissioning is a very important part of what we do. It sort of informs our design from the front end to the back end. So when we're designing, we get the lessons learned from our commissioning guys and say, you know what, this is what we saw, this is what didn't work, this is what we could design better to make sure that it doesn't happen on your next project. So with that, I want to introduce, which one did we start from? Ken Gao, one of our senior mechanical engineers at Merrick, was very instrumental in the design of the NBAC project and the New Zealand project and several others that we have going as well. And Eric Brad has been with us a slightly shorter time, but has an equally bright future at Merrick. So we're really pleased to have Eric, another one of our engineers with us. So with that, Ken, I'll turn it to you, and let you go from there.
Thanks, Brad.
Thanks, Mike. Here's my cell phone.
Okay, thanks. Quick bio, I was back in the South of mechanical PhDs. I actually both started out careers designing hospitals one of us several decades before the other on that side of the world. We put together this presentation based on some work actually two of our colleagues did looking at energy issues with directional airflow and the different methodologies for achieving different differential airflow and what impact that had on energy. At the end of the study, we discovered there wasn't actually a whole lot of difference, but it's a good way to look at some of the issues that face a ventilation engineer designing a laboratory. Because sustainability is pushing really hard on us to save energy, whereas ventilation is a really good way to use energy. So how does it impact this? Ventilation rates, differential airflow is up on an increased energy use. And behind all of this, laboratories are built to budgets, and there's not a lot of flexibility to spend money unnecessarily. This quote from FRaBSA, who's the engineering director at NIH, basis ventilation systems important to biosafety. Ventilation basics is two aspects to ventilation. One is removal at source. Best examples of that are fuel and biosafety cabinets, which are the primary containment for isolating aerosols in the way. And the other is dilution ventilation, which works quite differently. Dilution simply dilutes the contaminants in the air. So talk about air change rates. One key thing to realize here is that with an air change rate, the air's not exchanged totally each cycle. If there's perfect mixing, then you're really only diluting air to 50%. And then we have a quick look at the ventilation rate requirements. And the bottom line is there's no prescriptive requirement. There are some standards. But NFPA actually removed air change rates because what was found was that it's a slightly misleading concept as to how effective that is at removing contaminants from the air. However, IBC does mandate 1 CFM per square foot, which is equivalent to 6 air changes in a 10-foot high ceiling. NIH requires 6 air changes. USDA, I think, is 4 to 8. The ANSI standard basis it can't be specified. Well, I think the last word on this really should come from ASHRAE, who've done a lot of research and study on ventilation. ASHRAE is the American Society for Heating, Refrigerating, and Air Conditioning Engineers. And they found that increasing the air change rate from 4 to 8 air changes actually makes a huge improvement to the quality of the air. But going above 12 air changes produces diminishing returns. A lot of that is due to the actual way the air flows in a space. Once it gets up to 12 air changes, the direction of the air is more important than the actual route of it. But that would be a good over to Eric. I'm just going to talk about directional airflow.
Thanks, Ken. Yeah, I want to change gears a bit here and discuss directional airflow. Directional airflow builds on the principles of ventilation that Ken just spoke about, but it looks more at the coordination of the two and how they interact with each other. You can see a typical layout of a lab here. You have inward flows in your supply air. You have your exhaust flow. This can be fume hoods. This can be general room exhaust. This can be snorkel vents. You also have some acceptable recirculation of air within this room. I think it's important to note that in most, if not all lab situations, you do not want to have any recirculation from one lab space to another. The coordination of your inward flow and your exhaust flow can create what we call directional airflow. And here we have a quote from ANSI Z9.5 that discusses space pressurization or directional airflow. And the next couple of slides are going to be a number of different requirements about how they want space pressurization to act. However, I'd say that Sean's anecdote about the tissue digester is probably better at convincing you that you're going to want a negative pressurized space. But what directional airflow is defined here by ANSI. It's in order to limit the exposure of current hazards, and it opposes the migration of air contaminants. And one important point is it does not eliminate them; it simply contains them within the space. One thing that ANSI calls out here is that even with ordinary construction and a properly functioning ventilation system, the air can move briefly in the wrong direction. And while that's okay for ANSI, a couple of the standards we'll look at next will not allow that. So we start with the NIH CDC Biosafety and Microbiological and Biomedical Laboratories, or BIMBL. And it starts with a section on human DSL-3, where they require a ducted air ventilation system where you must provide sustained directional airflow into the labs from adjacent clean areas. And here the BIMBL says airflow will not be reversed. And one way to ensure that is using a visual monitoring device at the entry to each lab, which confirms you do in fact have negative pressure inside your lab. BIMBL also discusses animal DSL-3 labs, and again, the same requirement of inward directional airflow. This also calls out your ducted exhaust air, and that air is to be discharged directly to the outside without being recirculated. NFPA 45, which we should note is for laboratories using chemicals, not biological agents, also calls for a negative laboratory with respect to corridors and non-laboratory areas, but it also gives you three exceptions. One is a clean room, where that room you may not want your clean room to be negative. You actually want that to be positive, so that prevents any sort of contaminant from coming into the room. But they do require alternate means for preventing the escape of the atmosphere in the lab out into the corridors. And typically this is achieved through use of an anti room. The second option they give is that in a case like we mentioned earlier, you may have a momentary flow reversal based on ventilation system changes, door openings, fume hoods. That's slightly more allowable in the realm of chemical lab versus a biological lab. And thirdly, there are specially designated electrically classified areas that can be positive. From the NIH design requirements, once again, negative air pressure is required. This actually gives us a value. It says they typically we want to see about 100 CFM airflow from the corridor into your lab space. That's kind of a rule of thumb, which we'll talk about more when we discuss our energy study, but they do give that as an option. The chart you see here is a graph of the room pressure in a space when a door is open. So you see here it's tracking normally about a half inch negative. The door opens, you see a large spike, and now you have zero pressure differential as the door is open. The door is shut, and the system re-engages. Pressure drops significantly and then balances back to normal. And finally, from the USDA, we have the requirement, once again, of the air pressure being negative in the corridors. And notice this is not a very subtle theme we're seeing throughout all these different requirements. Once again, here they call for a directional airflow, and they give us more design numbers. They recommend either a 15% airflow differential between supply and exhaust. So your exhaust rate would be defined by your air changes per hour, and then you simply reduce your supply by 15% in order to induce a negative space. Or sufficient air exhaust to reach 0.05 of an inch of water column. And then they also recommend at least 50 CFM per door at all times. And these are the values that were used in the energy study that we discussed. Based on that previous slide, you see the two different options you have. You either have a percentage differential between your total room exhaust or your fixed offset per door. And these are two methodologies that are used equally, and there is some discussion over which is more effective. There's some concerns involving percentage offset. Variability in your supply and exhaust airflows could overlap and cause reversals. What that's saying is when you are tracking your supply based purely on your exhaust, those two airflows can change. And because many of your airflow control devices can have plus to minus 5% accuracy, if your exhaust goes too low and your supply goes too high, you may actually have a moment where your supply exceeds your exhaust in an airflow reversal. Thus, the number of 15%, which we saw with the USDA, which ensures that you still have a 5% band of safety. Percent offset typically is a Venturi valve because it provides more robust control and self-actuating, and it's pressure independent of your fan. So no matter what your fans are doing, it's able to deliver air reliably. In some larger rooms, you find that the percent offset airflow, so the difference between your supply and exhaust, is greater than what you can expect to infiltrate through a door, in which case you need to install these adjustable air leakage pads. So these are installed above the door, and they allow additional air to come into the room from the corridor and maintain your proper airflow offset. When it comes to having just a set flow per door, this achieves your set differential space without using any transfer openings to the wall. It's based purely on the crevice area between these spaces, and we say between spaces, we mean between the laboratory and the corridors. Now, in most tight construction, the only major crevice you have is around your door. Typically, all other openings in the room are sealed. In this case, the engineer specifies a CFM differential between the two spaces, and when the commissioning agent comes in, he or she will determine the actual offset required and rebalance the system. The ASHRAE chemical fundamentals suggest about 100 CFM per door will give you a differential of 5/100ths of an inch, and that pressure is not so much that it makes the door difficult to open. One thing we do see with rooms like this, because construction is becoming tighter and tighter, and sometimes even your door is not enough to provide, or when your door is installed, you have so little airspace that you have a very small offset required to meet your differential pressure. In which case you need very close airflow control because your offset may be only 30 to 40 to 50 CFM. One thing that helps is that there have been improvements in airflow control technology. Using pneumatic bladder dampers are one of the best sources for controlling airflow. And in some situations, it may make sense to add a small trim valve in parallel with your main valve. So your main valve acts as kind of a coarse adjustment, and that trim valve is more refined adjustment. We mentioned earlier we had a couple of colleagues who put together an energy study. The purpose of the study was to compare the two strategies, the percent difference in airflow and the offset airflow, to see if there was an appreciable difference in energy use. We did several calculations for different sized rooms, different air change amounts, different heat gains per room to see what the results were. We then took each of those models and set them up in 4 different cities, Atlanta, Denver, Seattle, and Minneapolis. And we compared the energy results. And as Ken mentioned earlier, they were not as conclusive as we would have hoped. You can see that with some smaller rooms, the requirement to use at least 50 CFM often overrode your 10 to 15%. So a large amount of the data looked like this, where everything just tracked exactly together, especially with rooms 200 square feet to 100 square feet. The location did provide an impact. That's not surprising based on the differences in climates there. You find that your outside energy costs are highly dependent on the location. Of the 4 cities we studied, we actually found that Atlanta had the lowest cost, Minneapolis was the most expensive, and Denver and Seattle fall somewhere in between. The results that we determined were that the location drove energy costs. A room with a higher thermal load is going to cost more to operate because your ventilation rates may actually exceed the amount of exhaust you need in space just to cool down the room. So you're running a lot of very hot process equipment. Even though all of your exhaust equipment only requires 1,000 CFM of exhaust, you may need to bring in 1,500 CFM suppliers to cool it all down, so then your offset pumps that exhaust even higher. Smaller exhaust rates obviously would correlate directly to lower energy costs, and larger rooms are going to cost more than smaller rooms. Also, the larger rooms, you can start to see a difference between your percent offset and your fixed offset. Our bottom line, 100% outside air systems cost money. As we discussed before, ventilation is expensive. And if you can design a system to use less ventilation, you're going to save money. Systems with a smaller offset may have decreased energy costs. We do want to offer special thanks to Jody and Victoria, who are the colleagues who did the study, and open the floor to any questions.
Actually, I have a question. Yeah, so being in Wyoming, just like South Dakota, North Dakota, a little bit of Kansas, Nebraska, it's nothing to have sustained winds of 60 knots for a long period of time. And working in my biophysical 3 lab, I sometimes notice it doesn't go positive, but the alarm will go because we have an analog that shows flow in case if something goes, the digital goes down, and then we have the digital, which sounds the alarm when that it reaches a certain level. What kind of systems do you put in place? Because I'm not an engineer, and I always wondered, because I noticed that when I'm working in there, even the biopsy academy sometimes will flip over from the green to the one red button or something, and maybe a little concerned, and then it flips back up, and I can always tell when the gust of wind stops. So, what kind of systems do you have in place that counter that?
Yeah, I think the bottom line here is that all mechanical systems have variability. And they're actually, the more modern systems are tighter than older ones. That was background of the study.
Sure.
But I think from an engineer's point of view, it's impossible to avoid those situations where the swinging in the control systems, and there's a lot of variables happening. It's not just the air valve or the room, there's a supply air valve, there's also a valve, there's also fan controls. There's the currents that's happening in other rooms will feed back to the ductwork. So it's really impossible to avoid those. The only advice I can give is to try and operate the lab as stably as you can.
I think they do a pretty good job up there. It's just, I've just noticed that it fluctuates when we have a wind event. So we're talking, she's a meteorologist, and she's always like, we have a wind event coming. So, but yeah, I've always noticed that in the lab, and I just thought I'd bring that up because we were talking about it.
What about
yeah, we have it's the latter. We have a lab, our lab, so I have a suite that I work in that is inside of the general area, which then is inside, then so I think it's 4 walls to the outside wall. That's what my lab is. If that answers your question.
Yeah, I know that doesn't lab where the dome is cascade, but one edge of the room is an outside wall.
Yeah, it's pretty much it's central in the building as you possibly get it.
Yeah. One of our colleagues was with the system before he joined us, designed a BSF4 lab for CBC. He said, just before it opened, it was all commissioned and set to go. The client took a group of scientists, eminent scientists, and all the alarms went off because they had a very serious overdose. And he said the bottom line there was they're taking 20 people in the space that was out of fire. And it's really doors open.
Sure.
It did take the dispatch. looking rational questions, I think. So that's the frustration of an engineer, I guess. You can design them using all kinds of, I guess we can design them and have all our numbers add up. When the system actually operates, it's like driving a car. You don't go straight up the road. It works.
Yeah. Thank you.
Yes, I was going to say one of the issues in looking at the high offset is the higher the offset between supply and resource, the more stable that system is going to be.
But it also costs more, right? It would also cost more.
Well, that's what we're looking at. The answer was if there's small rooms, not so much, because you need a high offset just to draw the claims. We designed vessels for the ag spaces which are airtight. We take a filter transfer ducts. Duct between the room and the node, we have a filter to try and buffer out that fluctuation. Whereas other people we work with designing vessel 4 will go for the univalve, which is a more accurate reactor, and rely on the accuracy of the electronic controls driving. If you open the bladder valve as a rubber bladder inside thin steel legs, it inflates and deflates, so there's a number of blades in each damper. Source of compressed air. Is that a question?
Yeah.
Yeah, it is compressed air. But in the leverage design, there's multiple air compressors on emergency power, and large air receivers to store air. But at some point, obviously, if there's a power failure, the emergency generators don't pick up, then it's all going to go soft, and the glass in dampers will seal off the spaces. Multiple systems that come with failure. And is there a possibility that all fail at once? Sure. But then there's plenty of costs.
Any more questions? All right, thank you.
We're good. Go.
So just to wrap a few things up here, if you haven't done so already,